Hi everyone. In this video we are going to talk about medians and centroid, and also we are going to see the properties of centroid. I have noted it as theorem number 5, and here we are going to discuss two main things, that the centroid divides each median in a 2:1 ratio, and also the medians divide the original triangle in 6 smaller triangles of equal area. And we are going to prove both of these theorems. Let's suppose we have a triangle ABC, as you can see in the diagram. For a triangle, a median is nothing but a line segment joining a vertex to the midpoint of the opposite side. Now here I am going to draw a couple of medians. I am going to draw one median from the vertex B and another median from the vertex C. And let's suppose the medians are BE and CD. So D is nothing but the midpoint of AB, and similarly E is also the midpoint of AC. Next I am going to join D and E with a line segment. Since D and E are the midpoints of AB and AC, then DE will be parallel to BC. We have seen that in the midpoint theorem. Next we are going to look at two triangles, the smaller triangle ADE and the original triangle ABC, and we are going to look for some similarities there. The first similarity between these two triangles is that the line segment DE is parallel to the side BC, and the second similarity is that angle ADE will be equal to angle ABC because they are the corresponding angles between two parallel lines. If we assume AB to be the transversal, then angle ADE is equal to angle ABC, and similarly if we look at angle AED, it will be equal to angle ACB because they are also two corresponding angles between the two parallel lines if AC is considered the transversal. And also angle A, or you can think of it as angle BAC or CAB, the angle A is a common angle between those two triangles. So between these two triangles we can see that the corresponding angles are equal. That means those two triangles will be similar triangles. Now that we have been able to prove that those two triangles are similar triangles, then the ratio of their corresponding sides will be equal. So here I have noted that AD over AB is equal to DE over BC is equal to AE over AC. That's the ratio of the corresponding sides, they will be equal. So from here we can say that DE over BC is equal to AE over AC, and then from there we can say that is equal to AE over 2 times AE because AC is 2 times AE, and that will be equal to 1/2. So since DE over BC is equal to 1 over 2, we can say that BC over DE will be equal to 2 over 1, which is actually 2:1. I just took the reciprocal. So BC over DE is actually 2:1, and we are going to use this information soon. So now we are going to look at two other triangles. Let's assume that the medians intersected each other at point G. Actually we use uppercase G to denote the centroid, and this point is called the centroid. Now we are going to look at these two triangles, triangle DGE and triangle BGC, and let's see what kind of similarities they have. Since DE and BC are parallel, we can say that angle DEG will be equal to angle GBC. Let me highlight the angles. Those two angles will be equal because they are the alternate angles between two parallel lines if we assume BE to be the transversal. And similarly, if we look at the other pair of angles, which are angle GDE and angle GCB, those two angles will also be equal angles because they are also a pair of alternate angles between two parallel lines if we assume DC to be the transversal. And then if we also think about the angle DGE and angle BGC, those two angles will also be equal because they are vertical angles. So now we see that between these two triangles the corresponding angles are actually equal. That means these two triangles are also similar triangles. So we can say that triangle DGE and triangle BGC, they are similar triangles. And because we have been able to prove that they are similar triangles, we can say that the ratio of their corresponding sides will also be equal. And from here, if we take the first part of the proportionality, we can say BG over EG is equal to BC over DE, and we have already proved that BC over DE is actually 2:1. So we can write it as 2:1, and from here BG is to EG is equal to 2:1. And that was the first part of the theorem where we said that the centroid divides the median in 2:1 ratio. Now here if you think about this median, the median BE is divided in 2:1 ratio by the centroid G because BG is to EG, that is now looking like 2:1. That means the centroid is dividing the median in 2:1 ratio. And similarly, if we take the second part of the proportionality, we can say that CG over DG is equal to BC over DE, and that is again 2:1. So from here we can say that CG is to DG, and if you look at the diagram, CG is to DG, the two parts of the median CD, that is also equal to 2:1. And similarly, if you draw the other median from vertex A onto the side BC, if you draw the other median, there also you will be able to prove that median is also divided into 2:1 ratio by the centroid. So that was the first part of the theorem. Next, we are going to see how to prove that the medians actually divide the original triangle into 6 smaller triangles of equal area. Let's do the construction first. Let's suppose we have a triangle ABC, and now we are going to draw the 3 medians from the 3 vertices. Here I have drawn the 3 medians, median AD and BE and CF. And let's assume that the centroid is the point G. Since we have drawn medians here, that means each of these points, like D is the midpoint of BC, and similarly E would be the midpoint of AC, and F would be the midpoint of AB. That means BD will be equal to DC. Similarly, CE will be equal to AE, and also AF will be equal to BF. So let me make a note of that. And now let's look at the 2 smaller triangles down below. The triangles are BDG and CDG. If you look at these 2 triangles, the first triangle's base is BD and the second triangle's base is DC. Now BD is equal to DC, right? So they have equal base. So let me make a note of that. And the second interesting point to note is that they both share a vertex. You see the vertex G, that is a common vertex for those 2 triangles. Now if there are 2 triangles having equal base on the same straight line and they share a common vertex, the area of those triangles will be equal. Now how does that work? Well, let's drop a perpendicular from the point G onto the side BC. I have drawn the perpendicular in yellow color, and let's assume that the perpendicular is GP, which landed at point P on the side BC. So now if you think about the area of the first triangle, what would be the area? Area of the triangle BDG will be equal to half times base times height. And similarly, if we think about the area of the other triangle, which is triangle CDG, that will be equal to half times DC times GP. DC is the base, so half times DC times GP. And also we know that BD is equal to DC, so these 2 quantities are equal right here. BD and DC, they are equal. That means their area is actually equal. So that means area of triangle BDG will be equal to the area of the triangle CDG, and let's denote that with a lowercase k, for example. So I am now going to denote it with a lowercase k. And using the same process, we can also prove that the area of the triangle CEG and AEG, they will also be equal. And let's denote that with a lowercase l right here. So I am denoting the area of triangle CEG and also the area of triangle AEG with a lowercase l to indicate that the area is actually L square unit. Like here I have denoted the area of triangle BDG and triangle CDG with a lowercase k. So k is actually in square unit. So we are saying that the area of the triangle BDG is equal to the area of the triangle CDG, which is equal to k square unit. And similarly, I am denoting the area of the triangle CEG and area of the triangle AEG with L square unit, right? Using the same process, we can also prove that the area of the triangle AFG and the triangle BFG, they will also be equal because they have equal base and they share a vertex. They have a common vertex and equal base on the same straight line. So they will also have equal area, and let's denote that with a lowercase m right here. And now if we think about the larger triangles like ABD and triangle ADC, for them also you see that they have equal base because BD is equal to DC and they share a common vertex which is A. So the triangles ABD and ADC, they will also have equal area. And similarly, if we think about the 2 other larger triangles which are triangle BCE and triangle BAE, they will also have equal area because their base is equal, which is CE and AE. They are equal base on the same straight line, and they have a common vertex B. So the area of the triangle BCE and the triangle BAE, they will be equal. Now because the area of the triangle ABD is equal to the area of the triangle ACD, can we then say right here, we can say that what is the area of the triangle ABD in terms of K, L and M? Well, ABD's area would be M plus K. And what is the area of ACD? Well, ACD's area would be K plus L plus L. And from here we can see that this K and this other K, they will cancel each other on either sides of the equal sign, they will cancel each other. So now we are going to be left with 2 times M equals 2 times L. And from here then we can easily say that M is equal to L, and that's an important result. Let me highlight that. And similarly, let's look at the next one where we have the area of triangle BCE. So BCE's area would be K plus L, and that is equal to the area of the triangle BAE, and that will be M plus L. And here again you can see that the L on the left hand side and the L on the right hand side, they will cancel out each other, and we are going to be left with 2 times K equals 2 times M. And from here we can easily say that K is equal to M. And I'm going to highlight this result also. And now if you think about it, we have been able to show that M is equal to L. That means those two areas are equal. And also we have been able to show that K is equal to M. So let me write it down. M is equal to L and we have K is equal to M. So from these two equations, we can clearly say that K is equal to L is equal to M. And that is the most important part of this theorem, that the area of each of these little triangles is actually equal. As we can see right here, we have been able to prove that K is equal to L and also L is equal to M. So essentially the area of each of these 6 smaller triangles, they are actually equal. And that's exactly what we needed to prove as part of the second part of this theorem. I hope everything made sense. Thank you for watching. See you in the next video.